last time we were talking about a spring mass system. Where say this is x equals 0, which is the equilibrium. And then the spring mass system oscillates back and forth. We used Newton's second law in order to derive the differential equation that looks like this, and this distance here being x of t, and that's changing from positive to negative and back. And so we derived the equation of motion that looks like this. Second derivative of x with respect to t plus k divided by m times x equals 0. And then we went about and we actually solved that differential equation, or at least we came up with a solution to it. The solution that we came up with was x of t equals a, where a is just some number, times the sine of square root k over m times t plus phi, where phi is some other number. Now, in this case, square root k over m, we gave the name omega. And I'm going to start today by talking about that. But just keep in mind what context we're talking about. This tells us where the block is at any given instant in time. It tells us how far away from the equilibrium position is the block. So you plug in t, you plug in the variables, you might have to figure out what phi and a are first, but you plug those in and then you get a number, and that's the distance. So let's just take an aside really quick. Why did we name square root k over m omega? Remember that omega was the variable that we used to describe the angular velocity of a system, right? Like the speed at which it goes around. And so there is a good reason for this. I'm not going to talk about it in detail because it's kind of an involved thing. It's not complicated. It's just a lot of writing. So I'm going to instead point you to section 8.1 and then the subsection total phase in the textbook. That will give you a nice overview as to why they're the same letter. Should be helpful. But the long and short of it is that we can model the motion of a mass moving in circular motion with angular velocity omega using this same function, but replacing square root k over m with omega. Like that's just, it turns out that if you model an object going in a circle with radius a, and angular speed omega, you can model its position. In fact, you can model its vertical position using precisely the same formula. So that's why we use the same letter, because they're very much two sides of the same coin. But just for now, just keep in mind that the omega that I will often write here is not it's not an angular speed. We actually will call it and I'll get to this, but it's not the it doesn't tell us how fast something is moving in a circle. It just has the same name as something that does. And we'll give it a different name in a minute. So let's just think back to the original system that we were talking about. So x of t is supposed to model the periodic motion of a mass on a spring. Yes, so it is different. That's the point. We gave them the same name because they, first of all, they have the same units, and but they're used in different contexts. There is a link between the two, but in the two separate contexts, they're kind of used in different ways. So this is all just to say omega is just a number here that's determined by the system. It's not something that like can change with time and so on and so forth. So x of t models the periodic motion of a mass on a spring. So great, now we know what where the mass is at any given time, but what else can we learn? Like what else can we learn from this solution? So we solved the problem, we solved an equation, we came up with a solution. What can we learn from that? Well, one thing that we could learn is we could learn the period of oscillation. So how long does it take to go through one oscillation, to go back and then forth again? So we can figure that out by looking at the formula. So we know that the sine of something repeats itself, right? That's just the thing. If you were to plot this, it would repeat itself every so often. The question is every how often? So the sine function repeats itself let me put, say, sine of theta. Sine of theta repeats itself every 2 pi, i.e. the sine of theta is equal to the sine of theta plus 2 pi, and the derivative of these things are also equal when you take when you add 2 pi and the second derivatives and the third derivatives and so on. So the functions are just identical if you shift them by 2 pi. So, but our function is not just sine of theta. It's a number times sine of something else. So all we need to do is we need to figure out when that something else, the stuff that is inside the sine function, is a multiple of 2 pi. So we really want to figure out the duration, how long between Ti and Tf, say the beginning and end of one period of oscillation, it takes. So we can do that by just taking the difference of these time periods, plugging them into the inside function, plugging them into here, and then setting it equal to 2 pi. And this should let us know how long the period is. T is Tf minus Ti. And so now we can just do some algebra and solve for Tf minus Ti. In fact, we find that omega times T equals 2 pi. And again, omega is the square root of k over m here. The reason why I'm using omega instead of square root k over m is because you get this sort of oscillatory behavior in a lot of other scenarios where it's not actually a spring. And so omega, while it still has the same property that it's the thing multiplied by t, and it fills the same role here, it might be written in a different way. It might not be square root of k over m. It might be square root of g over l or square root of gmm over something. Like it might just be some different combination of variables. So that's why I'm using omega here. So, and this was just by solving for Tf minus Ti. And so we find that the period of oscillation for any oscillating system, as long as we know what the omega is, T is equal to 2 pi divided by omega. And in this particular case, it's 2 pi times the square root of k over m for the omega that we know. So if you know what the omega is for some particular, actually, let me give it a name now. So here, the name of the omega that shows up in an oscillating system is angular frequency. It's no longer angular velocity because it doesn't actually tell us how fast something moves. It tells us how fast something repeats itself, hence the use of the word frequency rather than velocity. So what this really says is the oh yes, sorry. Yeah, that's m over k. Yeah, and I actually need to fix that in my notes. Yeah. Good catch. Yeah, so this tells us how fast the thing repeats itself, hence the word angular frequency. And it has units. It has the same units as angular velocity, but the units that it has, just to refresh your memory, is radians per second. And remember that radians are not like actually a unit, but they're a useful thing to carry around. Now, if we have angular frequency, this tells us the amount of radians that the argument of the sine passes through every second. We can also talk about regular frequency, which is just how many cycles does the function undergo every second? How many times per second does it repeat? And that's a little bit easier to compute, and perhaps it's a more intuitive thing to think about. The frequency is just omega divided by 2 pi. So keep in mind that 2 pi is one cycle, and so if you take the omega, which is how many radians per second, and divide it by 2 pi, that will be how many cycles per second. And conveniently, the frequency is just 1 divided by the period, i.e. if a period is 3 seconds, then you will undergo 1/3 of a period per second. So it's just a useful relationship. It tells us about how fast the oscillations occur. So I just want to give one word of caution here. When I say repeating a cycle, that does not mean how long does it just take to get back to where it started. Because if we go and we look at the spring, it'll go this way, or it'll pass through the center point twice as it undergoes one period of oscillation, right? Like it'll pass through, it'll be at this point when it's going left, and it'll be at this point when it's going right. And so that the time between those two moments is not one period. In order for it to be one full period, both the position and the velocity, including direction, have to be the same. So you could measure the period by figuring out how long does it take to go from in the center going left to in the center going left again, but you could not measure it as in the center going left, or the duration between in the center going left to in the center going right. That would be exactly 1/2 of a period, actually. So, okay, so we know something about the, so that tells us something about the oscillation, right? It tells us about how long the oscillation takes, how many oscillations occur per second, and so on. We can learn even more, though. We can learn about the kinematics of the system. Remember, kinematics tell us the position, velocity, acceleration, and so on of a system, right? So Friday, we solved the equation of motion for the simple harmonic oscillator to give us this equation. This is, again, just a refresher. X of t equals a sine omega t plus phi. And in this case, omega is square root k over m. So just like in the past, the way that we found this equation of motion was by, actually, let me back up. So when we were first talking about kinematics, we started with a constant acceleration, and then we integrated twice to find x of t. And we got something like x naught plus v naught x times t plus 1/2 at squared, right? This is the standard projectile motion kinematics. Now, because the acceleration was not constant in this case, the acceleration depended on where the object was, it wasn't as easy to just integrate the thing because it was just a little bit more involved. However, we could still find the position as a function of time. And similarly, we can find the velocity as a function of time just by taking the derivative. Similarly with the acceleration, because this stands for equation of motion. It's still true, even though the acceleration is not constant, it's still true that the velocity is the time derivative of position. And so we can take the time derivative of this function, x of t, and we get a omega cosine times omega t plus phi. And for the acceleration, you take 2 time derivatives of the position, or 1 time derivative of the velocity. And so this would be minus a omega squared sine times omega t plus phi. And so we can use this relationship, x of t, in combination with the velocity and acceleration to learn something more. In particular, we can learn about, for example, the maximum displacement. So just as how you could figure out, say, the maximum height that an object went using its kinematics by setting its derivative to 0 and things like that, we can also learn about like how far away from equilibrium does the object get at most. So the way that we would do that is we would figure out, we would realize that the sine of theta, the absolute value of the sine of theta is always less than or equal to 1, and the absolute value of the cosine of theta is also always less than or equal to 1. And so the maximum of any one of these functions occurs when the sine or the cosine is equal to 1. So in that case, we can kind of just read off the maximum value. The maximum distance that the object can be from the equilibrium is just a. Because if we look at this function here, the place, I'm getting to that, I'm about to get to that. The maximum, if you were to replace the sine of omega t plus phi with just the number 1, that's the biggest that sine could possibly be, which means that the biggest x of t can be is whatever multiplies that sine, which is a. So this is to say that this a here, this is the distance This is the distance that the spring was originally stretched. Because it's the maximum distance that the spring is from equilibrium. And we deduce that just by noting that the maximum distance is the distance that the spring was originally stretched to, assuming that it was released from rest. It has a name, and the name of that thing is the amplitude of the oscillation. It basically tells you how far the oscillation goes away from its center. Similarly, we could figure out the maximum velocity. The maximum velocity, we look at the velocity function, and then we see, well, this function is going to be maximized when the cosine is just equal to 1, because that's the maximum possible value that cosine can be, or -1. And so in that case, we can just read off what the maximum is. It's just a times omega. So we find that indeed the maximum velocity that this object can have is a times omega. And we could substitute in what omega is in this situation. It's square root k over m. And this just is the value of the maximum speed. Now I challenge you guys, you know how to figure out the maximum speed of the system by using energy conservation. Figure out the, using the fact that the total energy is 1/2 Ka squared, you can set that equal to the kinetic energy, because when the kinetic energy is equal to the total energy, that's the potential energy is 0. And so that's when the velocity is maximum. And you'd actually find that this is indeed the speed when the kinetic energy is at its maximum. And in fact, that occurs when the object is passing through equilibrium. So I challenge you to check that this is that this speed occurs when the object is at x equals 0. So the whole point of all of this exercise, sorry, is that once we have a description of the motion in terms of its position as a function of time, we can learn a lot about the system. We can learn about how far it moves, how fast it moves, how long it takes to repeat itself, and so on. And so being able to characterize a system in terms of this relatively simple formula, this simple harmonic motion, is a really good thing, because like over the course of 1.5 lectures, we've gone over the entirety, not the entirety, but very much the entirety of simple harmonic motion. And so if we can characterize other more complicated types of motion as an approximation of simple harmonic motion, then we're good. As long as our approximation is good, as long as like we're in a region where our approximation is valid, then we can just use the formulas from simple harmonic motion to just understand other more complicated systems. So we're going to do that right now. I'm going to give you an example of that. So we're going to talk about other oscillatory motion. And I'm going to show you how you can approximate that motion as a simple harmonic oscillator. So one example would be pendulums. Another example would be the oscillation of atoms and molecules. They oscillate back and forth like this, but it's not like actually a spring. So it doesn't exactly satisfy simple harmonic oscillation rules. So let's just work out a relatively straightforward example, which is a simple pendulum. So a simple pendulum is just a massless string connected to a massive point mass that hangs and swings back and forth, right? So we have our ceiling up here. We have our point mass attached to a massless string. And maybe it's traveling this way, and then it swings up to some maximum height. Call it theta max. And up here it has 0 speed, and then it falls back down and it repeats itself, right? And this theta changes with time. Call that distance L, say. So a priori, we can understand this system using energy considerations, but we don't yet know how to characterize its position as a function of time. That's not something that we've done yet. So, however, we do note that it does repeat itself, right? It just swings back and forth. Assuming there's no friction, it'll do that forever. So perhaps we can approximate it using approximate it as simple harmonic motion, and that's exactly what we're going to do. Now, in order to model it with the concept of simple harmonic oscillation, we have to understand the forces at play. So first, let's consider that a simple harmonic motion requires a restoring force, right? A one-dimensional restoring force. Now, this system is not one-dimensional. In fact, it's quite obviously two-dimensional. And similarly, the thing that does the oscillating is not like its height is not going positive and then negative and then positive and then negative. It's just going up and then back down to 0 and then back up. So perhaps thinking about this in terms of translational variables x, y, and z isn't the correct way to think about it, because the force here is not a restoring force. It's just the force of gravity and the force of tension. However, if you think instead of the motion in an angular sense, remember when we were talking about angular motion? Well, here we know that the torque that's applied by gravity about the pivot point, we know that that torque would be into the screen. I have to use my my left hand, but we know that the torque would be into the screen, and we know that the rotation, it goes left, it goes right, that could also be characterized as into and out of the screen. So in that sense, the motion is one-dimensional, but only if we consider the angular motion. We're not considering the vertical and horizontal position, we're considering the angular position of the pendulum relative to the vertical. So in that case, the restoring force is not a force, it's a torque. So let's figure out what the torque is. So we have our point mass. We have tension up and to the left. Sorry, that's kind of curved. And then we have the force of gravity downwards. Now this angle here is theta as a function of time, so it's just some arbitrary value. And so we can actually break this up into, we can break up the gravitational force into a component that points in the direction of the pivot point being up here. And we can break it up into a point that's perpendicular to that. So you guys know how to do this by now. The torque from the force of gravity is, oh, and sorry, we need to choose a coordinate system. So we need to choose which direction is positive and which is negative, just like we did for the harmonic oscillator, for the spring. We have to choose that right was positive and left was negative. Here, we're going to choose counterclockwise is positive. That way, when the mass is to the right of equilibrium, it will have a positive angle. When the mass is to the left of equilibrium, it will have a negative angle, and it's 0 in the middle. And likewise, this torque causes this torque would cause counterclockwise motion. Sorry, would cause clockwise motion, because it will cause the mass to rotate this way when theta is positive. So we know how to compute the magnitude of the torque here, and it's just a sign plus a magnitude because it's one-dimensional. So in fact, this is just negative r times f perp, where r is the distance between the point mass and the pivot. Now, f perp is this vector here. Sorry, not that vector. This vector here. And r is this distance, which we've already given a name. It's just L. So in fact, in terms of the variables of this system, the torque on the point mass is negative LmG times sine of theta. Right. Okay. So that's the torque. And so we can use Newton's second law, the rotational version, which says that the net torque. Oh, and by the way, the tension force doesn't exert a torque. It points in the same direction as the vector from the pivot point to the point mass. So, or to the place where it's applied. So it doesn't apply any torque here. So the net torque is just the torque due to gravity, and that should be equal to I alpha, where alpha is the angular acceleration. Okay, so let's substitute this in. So what we're left with is we have minus lmg sine theta equals I alpha, and now we have to use some more knowledge that we have. First of all, remember that alpha is the angular acceleration, which just means it's the second time derivative of the angle of the angular position. And for a point mass, a distance L away from the pivot, the moment of inertia is just ml squared. And so we can rearrange this to find the equation of motion of the simple pendulum in terms of the variables that we presented. Remember, theta here is a variable that changes with time. It tells us the angle of the pendulum over time. So the equation of motion that we get is d squared theta dt squared plus g divided by L times the sine of theta equals 0. That is the equation of motion. So notice that this equation of motion is similar to the equation of motion we had for the spring. For the spring, did I not write it down? I thought I wrote it down. Oh, here it is. For the spring, it was d squared, or it was the second derivative of x plus something times x equals 0. Here, it's the second derivative of theta plus something times the sine of theta. So it's not quite the same. It would be the same if instead of sine of theta, we just had theta there, but it's not quite the same. So unfortunately, even though they're similar, we can't just solve this by just assuming the solution that we had before and plugging it in and checking that it works. Like the solution to this equation is not a sine omega t plus phi. Like that just won't work. If you plug this in, it will not be equal to 0 for both theta and the second derivative of theta. But what we can do is we can take a look at this equation of motion and change it slightly where it's still approximately correct, but is simpler to solve. So let's look at what a plot of sine of theta looks like. So let's plot sine of theta. It looks something like this. Oh, that's terrible. Right, so we're plotting this thing. That's the thing that's giving us trouble here. If that was just regular theta, it wouldn't give us any trouble. So we just want to understand that function better. And so you'll notice if you were on a calculator and you zoomed in on that region near theta equals 0, you would notice that the function is very nearly linear near that region. And so, in fact, what this is saying is that for theta, again, theta is an angle here, measured in radians. For small values of theta, sine of theta is approximately linear. And if we could show exactly what the constant of proportionality is, then we could just replace sine of theta with a theta, right? Or with k theta, or with m theta, or whatever it is. And then we could solve it using the same tools that we used for the simple harmonic oscillator. Because a linear function means that it's just a number times the variable, theta in this case. Sorry, I'm just writing out some words. Remember, the SHO is the simple harmonic oscillator, which is described by that particular equation of motion. So we need to use a small angle approximation. And this is like a technical phrase. The small angle approximation has a very specific meaning. And it's often abbreviated using this symbol. We would write theta, or whatever angle it is much less than 1. That's what this double less than means. So we're going to take a detour before we can make that small angle approximation to understand how we do that. So let's take a detour to the realm of the Taylor series. Now, for those of you who have seen Taylor series in calculus, a lot of them, what I'm about to do should be like really easy and straightforward. But not everybody has seen that, so I want to make sure that everybody can see what we're doing. So let's say that we have a nice function, and nice is going to be in quotes. It has to have certain properties. For example, it needs to be analytic at the point of interest, and it has to be smooth, and so on and so forth. But don't worry about that. Everything that we deal with is nice. Suppose we have a nice function, f of x, that you want to approximate near x equals a. So for example, note Taylor series make everything nice. Polynomials are so easy to work with. So for example, let's say that you have the function what would be a good example? Yeah, let's say you have the function x plus 1 over 1,000 times x cubed, right? So if you had that function, the 1 over 1,000 x cubed term, if it wasn't 1 over 1,000, it would look like this. But because it's 1 over 1,000, the effect of that cubic term is not doesn't change the function a whole lot. So if you're looking anywhere near, say, x equals 0, then that x is the dominant thing. And so to approximate near x equals 0, in this case, a is just some number, not 0, then all it means is that we want to figure out a polynomial for f of x, or a polynomial approximation f of x, such that if you evaluated that polynomial, say when x is a plus 0.001, it's close to what it should have been. Basically, we're coming up with an approximation whose error gets bigger as you get further away from the place where you're making this approximation. So it turns out the easiest way to do this is with a Taylor series, and there are a lot of ways to do that, but I'll just give you the formula for the Taylor series, and you could derive it yourself if you wanted to, but I'm not going to make you do that. If you're given this function and you want to approximate it near x equals a, then your function can be approximated as the following polynomial. First, you take f and evaluate it at a. Then you add to it the derivative of f evaluated at a times x minus a. So far, this is just a linear function. This is a number. This is a number times x plus another number minus another number. Then you add to it f double prime evaluated at a divided by 2 times x minus a squared. Then you add to it f triple prime evaluated at a divided by 2 times 3 times x minus a cubed, and so on. And you would keep going. I'm going to do plus ... But you keep going. And so the point is as you keep going, your approximation gets better and better. But the terms in your approximation, the denominator here is 6, then the next denominator would be 2 times 3 times 4, which is 24. The next denominator is 2 times 3 times 4 times 5, which is 120. The next one would be 720. The next one would be 5040, and so on. So these denominators get really, really big, really, really fast. And so long as x is close to a, x minus a to high powers is close to 0. So these terms that you're adding, every later term, should contribute less and less to your approximation. It makes it just a teensy bit more accurate. But the whole point of this is that the leading terms, the terms with the fewest derivatives, are the terms that play the biggest role in your approximation. So this is what it means to Taylor approximate, or to write the Taylor series expansion of a function. You just evaluated it at wherever you want to expand it about, then you evaluate the derivative wherever you want to expand it about, and multiply that by x minus a, and so on. And so this will just end up giving you that f of x is equal to, say, c1 plus c2 times x plus c3 times x squared plus c4 times x cubed, and you could keep however high terms you want. But the point is it takes an otherwise complicated function and it spits out a polynomial, which is a lot easier to deal with as an approximation. So if we want to evaluate this approximation for x close to a, say x equals a plus 0.01, then let's just look at each term, at each of the terms raised to whatever power, what those terms give you. We would find that the first term, the one that has a power of 0, is a lot bigger than x minus a, which is 0.01, which is a lot bigger than x minus a squared, which is 0.01 squared, which is 0.001. 0.0001, sorry, which is a lot bigger than x minus a cubed, and so on. So you can see that the terms that are later on, the terms that are more complicated, get smaller and smaller, and so we can ignore them more and more. They're less significant. And so the whole point of a Taylor series approximation is that if you're close enough to where you care about, then you only have to keep maybe the first two terms. Maybe you have to keep the first three terms sometimes. But the point is it allows you to take a complicated function and replace it with just like a quadratic function, for example. That's precisely what we're going to do. We're going to use the Taylor series to approximate sine of x. So to figure out how to approximate sine of x, let's just, for small angles, remember, we're only interested in what happens when the angle is small. We can use a Taylor series to expand sine of theta near theta equals 0. So let's do that. So sine of theta, I'm just following these rules. First, I have to evaluate sine of theta at theta equals 0, because in this case, a is 0. So this is sine of 0. And then I add to it, what's the derivative of the sine? It's the cosine. So it's the cosine of 0 times theta minus 0. Then I add to it the derivative. So the second derivative of sine is the negative sine. So plus minus sine of 0 divided by 2 times theta minus 0 squared. And then I could do plus the third derivative of the sine is the negative cosine. So it's the negative cosine of 0 divided by 2 times 3, theta minus 0 cubed. And I could keep going. I'm not going to. And so we can actually, like, we know what the sine of 0 is. The sine of 0 is 0. The cosine of 0 is 1, and so on. So we can simplify. This simplifies to theta minus theta cubed over 6 plus theta to the 5th over 120 minus ... And so when theta is close to 0, when it's significantly smaller than 1, the first term, theta, is a lot bigger than theta cubed, which is a lot bigger than theta to the 5th. So the whole point of this is sine of theta is very nearly just theta for small angles. Note that, by the way, this is in radians. This does not work if you are using degrees. So just keep in mind, so when I say the sine of theta is theta, I mean, if you plug in, say, pi over 10 radians to sine of theta, then you would get approximately pi over 10 back. But if you plugged in 5 degrees, you wouldn't get 5 back. You would get whatever 5 degrees is in radians. So just as a check, and I challenge you guys to do this, if you plug in theta is 30 degrees, which is not that small all things considered, that's pi over 6 radians, which is about 0.52-ish radians. If you take the sine of 30 degrees, you get a half. So that's like less than 5% error. And that's for a relatively large angle of 30 degrees. So you can imagine that if we're just talking like, say, 5 or 10 degrees, that error is less than 1%. And so that means that we can, as long as we only consider a system that is oscillating at small angles, for a small angle system, that means that we can just approximate the sine of theta that showed up in our equation of motion with just a theta for a small angle pendulum, let's say. The equation of motion is approximately to maybe 1% error or less, d squared theta dt squared, and then we just replace the sine theta with just a theta and set it equal to 0. And so that's our new equation of motion. And now that just matches the simple harmonic oscillator equation of motion. It's the derivative of it's the second derivative of something plus a number times that something equals 0. It just matches it. We just have to make the appropriate replacement. And so we can solve this using the exact same tools and just by replacing the variables. So what we're left with is the angle as a function of time. Remember, the angle is changing with time, is equal to, well, we know that the coefficient in front is the maximum value, just like how the A in front was the maximum displacement from the equilibrium. So this is theta max times sine, and there's another typo in my notes that I need to fix, omega t plus phi. And now we just need to be careful. Here, omega is not k over m. It's the stuff that k over m was in the equation. And in this case, it's square root g over m. Sorry, square root g over L. And so what we can learn from this particular system, the period of oscillation, well, we know what omega is. Omega is square root g over L. So the period of oscillation for this system, i.e. how long it takes for the pendulum to swing, is 2 pi over omega, which is just 2 pi times square root L over g. And so now you know how you can figure out how long it takes a pendulum to oscillate. And so if you want to make a pendulum that oscillates exactly once per second, like the old clocks did, you just have to pick a value of L, which is just the length of the pendulum, that gives you 1 second for the period t. By the way, note that the mass on the end did not play a role at all in the period of oscillation, which is kind of interesting. It's just a consequence of the fact that gravity doesn't really, like the acceleration due to gravity doesn't really care about the mass of the object. It just cares about where the object is relative to the Earth. Right, so clearly we can use this simple harmonic model, or this SHO model, to deal with other more complicated systems. Now, so far, the system I gave you was easily describable in terms of a force, but not everything can be easily described in terms of a force. In particular, some things, it's more easy to describe the system in terms of a potential energy. So let's see if we can actually do this same type of approximation if we only know the potential energy of the system and not the forces. We don't have a force diagram. We're going to do the same trick for the pendulum, but we're going to just use only its potential energy, not its not the forces. And the answer is, of course, yes. Otherwise, I wouldn't tell you about it. So for the simple pendulum, again, let's draw it out. And we can figure out what the gravitational potential energy is of the system, because it is just that is the only potential energy here. The tension force does not produce potential energy. So we have our pivot, we have our mass, some angle theta relative to the horizontal. Say this is our equilibrium point. So when it's swung in angle theta, how much potential energy should it have? Well, if that distance is h, this distance here is L, and this distance is L, then that h should be equal to L minus L times cosine of theta. And I'll leave it to you guys to figure out why that's the value of h, but it boils down to just some simple trig. And we're going to call this height y equals 0. So the potential energy then, for any given theta, would just be this number times mg. That is, of the potential energy as a function of the angular position theta is just mg times L minus L cosine theta. So now let's write down what the total energy of the system is. Well, we know how to write down the total energy of a rotating system, right? The total energy of a rotating system is 1/2 the rotational, or is the rotational kinetic energy, 1/2 I, and I'm going to write the, instead of using omega squared, I'm going to write the time derivative of the angle squared, just because I don't want to use the letter omega twice, plus the potential energy, mg L minus L cosine theta. And so you can see right away that this is just written in terms of the derivative of theta and theta itself. So just as a quick reminder, for the spring mass, the potential energy is pretty easy. The total energy is 1/2 times m, the mass of the mass, times the second, or times the derivative of the position, which is just the velocity, squared, plus 1/2 times k times x minus the equilibrium position squared, right? That just is the formula for the total energy for spring mass. So what we're going to do, or what we're going to try to do, is we're going to try to approximate the total energy here so that it matches the total energy here. And then we can just match variables, and then we can just, once they match, then we can just assume it has the property of the simple harmonic oscillator, and then we're done. Pendulum. So again, we're going to use the small angle approximation. However, we're not approximating sine of theta anymore, we're approximating cosine of theta. And we're going to replace the cosine of theta in this energy with whatever we approximate it to be. So we have to use the Taylor series again. And this time we would find that the cosine of theta is approximately equal to the cosine of 0 plus, what's the derivative of cosine? It's the negative sine of 0 times theta minus, and we're approximating it when theta is close to 0, so theta minus 0, plus the second derivative of cosine at 0 would be negative cosine of 0 divided by 2, theta minus 0 squared, plus dot, 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 so on and so forth. And so we can just evaluate this. We know what cosine of 0 is, what sine of 0 is. This is just equal to 1 minus 1/2 theta squared. Yeah, this, everything is in radians when you're dealing with the argument of a sine or a cosine. It would be plus 1/24 theta to the 4th minus dot, dot, dot. And so for small theta, cosine of theta is approximately equal to 1 minus 1/2 theta squared. So by the way, just as a point, I'm almost done by the way, and then we'll call it. The reason why we're keeping the second term, whereas for the sine we just kept the first, was because if we only keep the first term for the cosine, it tells us that there is no dynamics at all, that the potential energy doesn't change at all. So we want to keep the lowest, we want to keep enough terms so that it still changes without making it overly complex. So that's why we keep up to this first non-constant term. And you'll find that we do this a lot for Taylor series. And so we plug in. So what we're left with is that the E total is 1/2 I d theta dt squared plus, and you can do some simplifications here, plus mg L minus L times 1 minus 1/2 theta squared, which is equal to 1/2 I d theta dt squared plus mgl over 2 times, and I'm going to put in a 0 here that doesn't need to be there, 0, or theta minus 0 quantity squared. Assume that we're always working in radians, just always. Everything is in radians. Imagine that degrees don't even matter, because the argument of a sine, the stuff that you plug into a sine or a cosine, should always be in radians. And so importantly, this matches. It matches the energy of a simple harmonic oscillator. In this case, theta equilibrium is 0, which is straight down, which is where we expect the equilibrium to be for a pendulum. And we can match the other variables too, or the constants rather. So in this case, where for the simple harmonic oscillator, there was the variable m, we have I. So we have m corresponds to I. I'll put pendulum here. And I'll put SHO here. For instead of dx dt, which is the speed, we have d theta dt. Instead of k, we have the variable mg, or we have the combination mgl, because it was 1/2 times k times x minus x equilibrium. Instead of x, we have theta, and instead of x equilibrium, we have 0. So what that means is all we have to do is take the formula from the effective, or from the simple harmonic oscillator, and then just replace all the variables. So in particular, the effective spring constant of the system is K effective, which is just MGL. So if we were treating the system like a spring, the spring would have to have spring constant MGL. And then we can figure out the period. Well, we know the period of a simple harmonic oscillator. It's 2 pi times square root of the mass divided by the spring constant. So we just need to plug in the appropriate variables. So this is 2 pi times the effective mass of the system, or 2 pi times the square root of the effective mass of the system divided by the effective spring constant. And the effective mass is just the moment of inertia. The effective spring constant is MGL. So the period here is 2 pi times the square root of I divided by MGL. But notice that, again, like before, I is just ML squared. So the period is really 2 pi, it simplifies, L over G, which agrees with what we had before. So the takeaway of this whole business, and I'll be done in just a minute, just have a little bit more to say, is that if you can write the energy of any system so that it matches, it has this property where it's 1/2 times some constant times the derivative of something squared, plus 1/2 times another constant, 1/2 times another constant, times that thing that you took the derivative of minus a number quantity squared. If you can write any system so that it matches by using some sort of approximation, so its total energy matches, (1/2) m effective times z is just some variable, whatever it is. In the simple harmonic oscillator, or in the pendulum case, it was theta, plus 1/2 k effective times z minus z equilibrium squared. If you can do that for some variable z, then you can use all of the results that we had for the simple harmonic oscillator, this a sine omega t plus phi business, for that system. And so as long as the system that you're describing lives in the region where the approximation is valid, in this case, in the case of the pendulum, that just means that we're only concerned with small oscillations, not like really wide oscillations, because in that case, theta would not be small. As long as you're living in a regime where the approximation holds, then approximating the system with the simple harmonic oscillator is a valid approximation. So this is all to say, no, so this is not, so pendulums are not really a 2D oscillation. It's still a 1D oscillation. It's one dimension and angle. This is all to say, here's a hint for the homework. This is the process, matching total energy. for problem 3C and 3D. And the potential energy that you're modeling here is the effective gravitational potential energy that we talked about last week. This is the one that has the L squared term as well as the GMM over R. All right, so I'm going to end the lecture there. Sorry, I ran over.